Now, moving on to talk about the gas chromatography. So, usually there are two types of chromatography. There is the gas chromatography and the high performance liquid chromatography, or HPLC. So, in gas chromatography, now the mobile phase is going to be a gas which is called the carrier gas. This carrier gas can be hydrogen, helium, or nitrogen. And then we have a stationary phase, and the stationary phase here can either be solid or it can be liquid coating a solid. So in gas chromatography, we inject our sample, which must be either a gas or a liquid that has to be evaporated completely inside the after it has been injected. So the whole system must be at work at high temperature. So we inject our sample and it's evaporated, and then we supply the mobile phase, which is the carrier gas, which will take the sample through the column, and the different component of our sample will be separated, and then we will eventually get our chromatogram where the different component will be eluted from the column at different times. So in gas chromatography, as I said, the carrier gas can either be hydrogen, helium, or nitrogen. These three carrier gases must be all are inert gases. They do not interact with our solution, with our sample or our components, and they can work efficiently, and they can carry our components through the column to reach the detector. The stationary phase can either be non-volatile liquid that is attached to either directly to the column, or it can be attached to a solid support, or it can be a solid stationary phase. In case of the liquid, this is called the gas liquid partition chromatography. In case of using solid stationary phase, this is the gas solid adsorption chromatography. So we either use partition or adsorption. As I said, as the whole the sample our sample must be volatilized, so it must be volatile. So the whole system must be kept at high temperature all the time. And as the different component reach the detector, there must be also volatile. So even the detector is kept at high temperature as the whole system. The carrier gas can be hydrogen, helium, or nitrogen. The, um, the, the most important thing I want you to know about the carrier gas, this carrier gas, that helium is the most commonly used gas. And why helium? Because this is the one that is mostly compatible with the detectors. So most detectors are compatible with helium. Some of the detectors are not compatible with hydrogen or nitrogen. So it depends on what detector you are using in your gas chromatography that will tell you which gas you can actually use as your carrier gas. All of these carrier gases have the same optimal plate height, which is zero point 0.3 millimeter. This is the optimal plate height for all the three, but at different flow rates. Hydrogen and helium give better resolution than nitrogen, but at higher flow rate. Because mostly the solutes will diffuse quicker with more rapidly through helium and hydrogen than it does with the nitrogen. Now moving on to talk about the column. So there are two different types of column when it comes to the gas chromatography. There is the open column and there is the depacked column. So what is the difference between these two types of column, and how does this affect the whole process of our separation? So the open tubular column This is there are two types of open tubular column. So there is the wall-coated open tubular column, and wall-coated is simply when you have a liquid, viscous liquid that is non-volatile, and this liquid is attached to directly to the walls of the column, and it's an open column, so it's not packed. Okay, so this is the open tubular column here, and you have your liquid, which is your stationary phase, attached directly to the walls of the column. And we have another type of open tubular column, which is called support-coated open tubular column, or SCOT. So this type, there is also a liquid stationary phase, but this liquid stationary phase is not directly attached to the walls of the column, but rather to a solid support. So you have a solid support, which is not your stationary phase in itself, but it's just a solid support attached to the walls, and then the liquid stationary phase is attached to that solid. So this is the support coated open tubular column. The normally the diameter of if we have a high diameter of our column, the column must be very small. So the diameter, if it exceeds 0.3 2 millimeter, that will tend to overload the vacuum system of the mass spectrometer. Most gas chromatography are attached to mass spectrometer. So we try to use columns that have a small diameter. The effect of the open tubular column diameter on resolution, the smaller the diameter of the open tubular column, the better the resolution. And you can see here in these two chromatograms that the first one on the left, the diameter of the open tubular column here, the inner diameter is 0.3 millimeter, while for the second one on the right is 0.2 5 millimeter, and we have two different components we are separating. If you look at these two chromatograms, you will find that for compound 1 and 2, they are better separated here on the open when the diameter is smaller, so it's better resolution here. So we use a smaller size or smaller diameter of our open tubular column, so it affects the resolution. Uh, Generally speaking, the solid coated, the support coated open tubular column, the Scott one, can handle larger sample size. And then we will see for the packed columns, it can handle even larger size of the our sample. The inner diameter, the range of the inner diameter for the columns are typically between 0.1 and 0.53 millimeters. So this is the range between 100 and 530 micrometer, and the length between 15 and 100 meter, and the average size is around 50 meter. This is the most common one. So the packed column, so the other type, which is the packed column, it's more like the normal column we will see in the high performance liquid chromatography. So it's completely packed, and then it's not open from inside. And then we have the stationary phase can either be solid or it can be liquid that has that coats a solid support. So you either have a solid particle that are coated with a liquid, viscous liquid that is non-volatile, which will act as your stationary phase, or it can be completely packed with just a solid as a stationary phase. Compared to the open tubular column, the packed column will have a better or greater sample capacity, so you can add more sample or you can handle larger quantity of sample in comparison to the open tubular column. But they have this advantage of giving broader peaks longer retention time, and less resolution. So when you think about it, why would we use the packed column? It gives us several advantages. The one of these advantage is that we can use it with larger quantities. So we can use it for preparative separation. So preparative separation means that you separate your component and you want them separated. It's not just for qualitative and quantitative, but also for preparation. So if you have, for example, if you are making or synthesizing something new and then you want to separate the component and purify them, you can use preparative GC to separate these components completely, and you can have each and every one of these in a pure form. So when you need your separated component, this is called preparative when you get them, and the backed columns are the best one that will serve this need. Also, we can use it to separate gases that are poorly retained. So if because it has higher retention time here, as we said, so our longer retention time. So if these are poorly retained, if your components are poorly retained on the column or on the stationary phase, we can use the packed column. Now moving on to the final thing about the gas chromatography, which is the separation process in gas chromatography. So what is the elution order in gas liquid chromatography? So the elution order in gas liquid chromatography will depend on two things. The first one is the boiling point of our solutes. The second one is the interaction between the solutes and the stationary phase. So if you have different components in your sample and they vary greatly in their boiling point, then they can be easily separated from each other using gas liquid chromatography, and the choice of the stationary phase here will not be a big problem. You can use any stationary phase to elute these different components because they can be easily separated based on their boiling point. The second thing is um, if you have the different components have similar boiling points or the boiling points are very close to each other, then it would be difficult to just separate them based on their boiling point because they will be eluted at the same time. So you have to use now the interaction between the different interaction between the solutes and the stationary phase. So the use of the stationary phase will be very important. The main criteria of choosing a good stationary phase, the stationary phase must not react, of course, with your solute. It must be inert to your solute. It must be thermally stable. Remember, the whole system works at high temperature and must have low volatility, and the polarity of your system must be appropriate for your sample components. Why the polarity is important? Because the choice of the stationary phase here will be based on like dissolves like. What do we mean by like dissolves like? That means if you have polar components, then you tend to use polar stationary phase. And if you have nonpolar components, you tend to use nonpolar stationary phase. Because if you use polar stationary phase and your component that you want to separate in your sample are nonpolar, they will not be retained. They will be eluted quickly out of your column and vice versa. So if you are using, you want to separate different non-polar component, you have to use non-polar stationary phase. And if you use polar components, you have to use polar stationary phase. The retention of the polar and nonpolar solutes will change as the boiling point of the solute changes and also as the polarity of the stationary phase changes. So let's have a look at these two chromatograms. So we have a list of components here. These are all solvents, and as you see, these solvents vary between hydrocarbons, which are nonpolar, and ketones, which are middle in polarity, and then you have some alcohols like pentanol, like butanol, like propanol. So if you look at these, you're going to find that they are different in their polarity. So the alcohol are the highest in polarity, and then you have the ketones, and then finally the hydrocarbon. So if you, the chromatogram on the left is the one where we used non-polar stationary phase. So when we use non-polar stationary phase, you will find that these different components were separated based on their boiling points. And the based on their boiling points, and also the most non-polar component will be separated at the end, because this is non-polar stationary phase. But when we use this polar stationary phase, you will find that number 9, 6, and 3 here will be equivalent to the pentanol, uh, butanol, and propanol, which are the polar components here, which are the alcohols. So they have been retained for longer on the stationary phase, and you even can see that they have been eluted at around 18 minutes, and around 9 minutes and like 5 minutes. So they retained longer. But again, if you look, that number 9 is the highest one in boiling point. So pentanol is the highest in boiling points, and then you have the butanol and propanol. So 3 propanol, because it has the lowest boiling point, it was eluted first, and then the butanol, and finally the pentanol, it has the highest boiling point. So you can see now the effect of both the boiling point and the effect of the polarity of the stationary phase on the elution of your different component. There's something called temperature and pressure programming in gas chromatography. So let's say that you have so many different components you want to separate in your sample, and they vary greatly in their boiling point. So you would say that the components that have very low boiling point will be eluted fast. But if you have components which have high boiling point, they will be retained for a long time. So in order to reduce the retention time for these, you can then increase the temperature of your system. But this is a programming thing. So you don't keep one temperature, but you vary the temperature as you move as you go ahead with your analysis. So you start first with a certain temperature of your system until the first component are eluted completely, and then you increase the temperature of your whole system, so the component which have a high boiling point will be eluted faster. So this is called temperature and pressure programming. Finally, detectors in GC. So the ideal detector must have several desirable features, like it must have a low detection limit, um, a linear response over a wide range of solute concentration, so we can make the quantitative analysis work easier for us. And it must be sensitive. It has good sensitivity for our solute, or it can be selective for a specific class of solute. Also must have insensitivity to change in flow rate or temperature. So when you change the temperature, we don't want our detector to change its sensitivity. So must be stable with the change in the temperature. Though there are some examples of the detectors that we use in a GC. The most common one that we use is actually mass spectrometer, and you will find so many different analyses for and papers published. People have been using the GC with